Hey all, and welcome to the next lecture in the Practical Packet Analysis online course. This lecture is called Tapping into the Wire, and it's all about the physical process of capturing packets. After all, you can't analyze packets until you've collected them, and collecting packets can be a non-trivial matter. Sure, you can install Wireshark on your desktop and collect packets right away, but what if you want to collect packets from a machine without Wireshark installed on it? Also, what if you suspect the machine has malware installed and you don't want to physically touch it? For that matter, if you're performing a penetration test and you don't want the user to know you're collecting their packets, how would you do that? I'll answer all these questions by discussing a number of different packet capture techniques, or as I call them, techniques for tapping into the wire. In this lecture, we'll discuss a number of techniques for collecting packets on the wire based upon your specific situation. And there are a lot of different scenarios in which you would need to capture packets that need to be considered. And we'll discuss a lot of those and conceptualize how you can characterize your specific situation and what to do about it. Now, to support that discussion, we're also going to talk a little bit about networking hardware, so switches and hubs and routers, and how those play into the art of capturing packets and what limitations they provide. So that'll be a little bit of a basic networking lesson to some degree, but we'll talk about that in a lead up to the discussion about sniffer visibility windows. So when we sniff and capture packets, we're concerned about what visibility we have, and it's the networking hardware that's really going to make or break our visibility and determine how we need to go about capturing packets. Based upon that, we'll talk about different capture techniques. And once we've done that, you should leave this module with an understanding of how to capture packets in nearly any scenario. Of course, the rest of this online course will be devoted to analyzing packets. So if you want to analyze your own packets, you should definitely pay attention here and maybe even try out a few of the techniques I'll show. Some of them I'll just talk about and conceptualize and show some diagrams, and a couple I'll actually demonstrate, such as ARP cache poisoning. I'll continually reference the techniques here as we go into the practical examples throughout the course. So I may go through a scenario and present a problem state and say that I'm going to collect packets by using a span port or using a tap. And understanding what I mean when I say that is going to be important to understanding the perspective of where those packets were captured from and what data may be there and what data might be missing. So this is certainly an important lesson if you're not familiar with how to capture packets, because we're going to talk about all those different scenarios and why they matter for when you do the analysis of those packets. Now, the thing we know here is that in order to analyze packets, you have to collect them. Certainly, in many cases, such as in this course, you'll be provided with already collected packets. So a packet capture file that contains packets you can load into something like TCP dump or Wireshark. But absent that, TCP dump and Wireshark don't really do anything unless you feed packets into them and unless you collect them on your own. So in this case, we want to talk about ways you can collect packets and the strategy that goes into that. And I mentioned strategy because strategy is an important facet of this. And there's really three questions you're going to ask when you determine how to collect packets, how to get them into your analysis tools. And it's going to depend first and foremost upon why you're collecting packets. What is the goal you hope to accomplish? Certainly it just may be for a fun exercise or maybe for a learning purpose. But when we talk about practical application of the knowledge you're gaining here, we're talking about why you would be collecting packets. And there are a couple different things that might come to mind here. First and foremost, you might be troubleshooting something. This is going to be the most common task for system or network administrators. And it's going to happen particularly with network-related issues when a user calls and says, hey, some function is not working for me. I can't connect to something. An application is not working. I'm getting this strange error, all those sorts of things. So we're talking about troubleshooting both from a user perspective and also from a network perspective in terms of, building out or growing or expanding or changing the configuration of your network. Troubleshooting issues at the packet level is going to be an important part of what we're talking about and learning in this course. So that might be a reason you're collecting packets. Next might be monitoring performance. The most common thing I've ever had said to me when working in a support role is the network's slow. Well, is the network really slow, or is it something different? Is it maybe the application slow? Maybe the remote server that we have no control over is slow. Maybe the user's computer is so loaded down with malware that that's why it's slow, or maybe the user's just doing something wrong, or maybe it's a high stress point of the day. A lot of users are doing a lot of things. Definitely numerous reasons why a user could be experiencing slowness, and monitoring performance is a big reason why you might want to collect packets for a number of ways. So that could also be not just on the system level, but even on the application level. So if you're a programmer or a developer and you're testing or debugging an application that's performing slow over the network, then monitoring performance might be a reason you're collecting packets there as well. Next is the security purpose for collecting packets. And we talk about network security monitoring and incident response. This could be the collection of packets proactively, which is what we're talking about when we say network security monitoring. In this case, we're collecting packets continually on a 24/7 basis and storing those for some period of time so that they can be used to investigate security threats, maybe even for some type of network-based intrusion detection system or so on. So that's a much higher performance type of packet capture scenario, and it brings with it specific requirements that have to be addressed. So these are all three reasons, probably the three most prevalent reasons why you might be collecting packets, but certainly there are others as well. So that's why you're collecting packets. The next question is, where is the host or host located from which you're collecting packets? So, for instance, if you're troubleshooting an isolated issue, you may be talking about a single host. It could be a computer, it could be a printer, it could be a router, it could be any number of things. The same for monitoring performance. If you're talking about network security monitoring, you might be talking about an entire network segment, so the entire research department or the entire finance department. Or in many cases, you might actually be talking about your entire network, so the whole thing, every department, every computer responsible for collecting packets at a network egress point. So where hosts are located is an important consideration when you talk about collecting packets, and that's going to come into play when we think about visibility windows. So if I'm collecting packets with a packet sniffer, I want to know, does the placement of my packet sniffer, is it correct for the visibility I need to see all the communication for these systems? If you want to see all of your systems on your network and their communication out to the internet, you need to be at that network egress point. If you only want to see a certain segment, you can actually be lower down, more inside of your network as opposed to that egress point right there. So that's going to be a big concern and something we have to talk and think about as well. Finally, what technology do you have available? And this certainly relates to visibility windows, but specifically it relates to networking hardware. When you want to capture packets, it definitely matters whether you're connected to a switch with a certain number of capabilities, or if you have maybe a network tap you can use. If you have a tap, great, that's something you can put in line. If you can take systems offline, maybe you can install a tap. Maybe you have a switch that supports span or monitor mode, and you can just configure the switch to send packets to your sniffer. If it doesn't, maybe you have to get a little more creative. Maybe you have to use a technique like ARP cache poisoning. So there are a lot of different techniques, and it's to some degree going to depend on what technology you have available and what networking gear you're working with. So these are all different concerns when we talk about the strategy for collecting packets, and generally you need to be able to answer all three of these questions. So for the rest of this particular lesson, we're going to talk about these things. Next up, we're going to talk about networking gear. So we're going to start with this third question. We're going to move to visibility windows from that, and we're going to talk about visibility windows related to networking gear. And finally, I'm going to describe various different techniques for collecting packets, when you would want to use each one, and we'll actually end with a flow chart I've provided that you can work through to determine what is the best manner to capture packets at any different point in time. And we'll provide that to you as a PDF you can use as well. So let's dig into this and let's get going and talk about networking gear. When I use the term networking gear, I'm talking about the connectivity hardware that's used to connect networks together. And that's generally done with a combination of hubs, switches, and routers. In more modern terms, specifically just switches and routers, we don't really see hubs as much. But hubs, you will still see them occasionally in some environments where they're just old and haven't been replaced for quite some time. We'll talk a little bit more about why that is later. But ultimately, you need to understand the function of what hubs, switches, and routers do and how they work together. Of course, hubs and switches are used to connect devices to a local network, and routers are used to connect one network to another network. So just by accessing this course online, you're probably traversing at least one switch on your network. Maybe it's a switch that's built into a router, but one switch nonetheless. And then you're traversing several routers across the internet, and maybe a few switches along the way, or one on the receiving end as well. So you're using a lot of this equipment now if you don't realize it. And we're going to talk about each of these three things and why they matter so much for packet capture. Of course, I have some images of them on the screen here. We see a simple, small home hub with 4 ports. We see a larger commercial switch, a Linksys branded one with a whole lot of ports. And then we see an enterprise router, something you might find in a medium or large size organization, in this case a Cisco brand router that would probably sit in a rack somewhere along with a lot of other networking gear, probably a lot of switches and routers to be found together that look like this. So let's start with hubs, which are really the simplest form of network connectivity device. And when I say simple, I'm talking about a basic repeating device. And I want to illustrate that based upon the figure you see on the screen here. In this figure, we have 4 computers, computer A, B, C, and D. And computer A is attempting to communicate with computer B. To do that, it sends data, so it sends a packet data or network traffic to computer B, and it sends it through the hub. Now, what the hub does when it receives it, obviously computer A is connected to a single port, is it takes the data it receives on that single port and forwards it to every other port on the device. So it actually forwards the traffic to computer B, C, and D, even though it's only destined for computer B. Now, in this case, ideally, only computer B accepts that data, but computer C and computer D theoretically could if they wanted to. And of course, this is obviously fairly inefficient. This is what we call broadcast communication. Now, there's a type of broadcast communication that we can do at a software level where we intentionally send things to every device on the network, but this is hardware broadcast. That is to say that, again, no matter what device computer A is sending to, that data is actually being transmitted to every device that's connected. And if there's another hub connected to this main hub, the same deal. It's going to be forwarded to the other hub, which is going to send that to every device connected to that. So that's broadcast communication from a hardware perspective. Now, as you might imagine, that's not the most efficient thing. It's very cheap, it's very simple, but it's also very inefficient. And it's inefficient for a couple of reasons. One is that most hubs are generally unidirectional. That's to say that computer A can only send information or receive information from a hub. It can't do both at once. So it has to send and it has to wait. And when you talk about sending, if computers A, B, C, and D are all sending data at the same time, and there's only such an amount of traffic that could go through the device, you have the opportunity for collisions. And you think of that just kind of like what it sounds like, packets colliding due to a limited amount of circuitry that can be used to transmit that data between the different hosts. So collisions ultimately result in packet loss, and that's kind of the enemy of good packet capture is, you think you're getting all the packets and you open the file and things are missing and you're making assumptions and making conclusions based upon incomplete data. So collisions and the concept of being unidirectional, only having unidirectional instead of bidirectional traffic, make hubs incredibly inefficient, which is why for the most part you don't see them anymore. You don't see people manufacturing and selling hubs anymore, and you really have a hard time finding them. Again, I still run into them occasionally, especially in school districts. I see them a lot, or in old government facilities where they're just sitting in the back of a closet and haven't been replaced, and maybe they only have a couple of devices connected to them. Generally, if you have a lot of devices connected to hubs on a network, you're going to know it because things are going to run incredibly slow, and you're going to have a lot of inexplicable issues related to all the collisions that might be occurring. So we don't see a lot of hubs, but hubs are important to mention because they are kind of, again, the most basic type of networking gear, and they actually do make packet sniffing really easy. And to demonstrate that, I want to introduce the concept of the visibility window. That's what we see on the screen here. So this is the same image for the most part that we had on the last screen. We only have 3 computers here. We have computer A, computer B, and computer C. And then we have a 4th computer, which is actually our sniffing device. And the purpose of this image, and we'll have several other visibility window images later, are to demonstrate that when connected to a hub, here are the packets you are able to collect. Right? Here are the communications you can intercept between different devices. And in this case, since we have a hub, we can see basically everything. If computer A wants to send to computer C, that data is going to computer B as well. And it's also going to our sniffer. If computer B wants to send to computer A, it's also going to computer C in our sniffer. Hubs are really a dream from a packet capture scenario because simply by virtue of plugging into the hub, you're going to be able to see and accept packets going between all the different machines. And that's why in this case, our visibility window encompasses everything. So it's encompassing computer A, B, C, and the link going to our sniffer. The physical sniffer itself is existing outside the little yellow box, but the link itself is within it, demonstrating that, again, we're seeing everything here. So this is the concept of the visibility window, and this is going to change as we move into looking at switches and routers as well. But whenever you capture packets, you want to keep visibility in mind, and thinking of your network diagram in terms of a visibility window is a really easy way to do that. So again, hubs, very simple devices. You don't see them a lot anymore. They make packet capture very easily because really you just plug into them and you can see communication between all devices. It's going to get a little more complicated when we talk about switches here in a minute, but understand that hubs, again, very, very simple. Moving on from hubs, we move into switches, which are really designed kind of as the modern replacement to a hub. Again, you won't find hubs in most modern networks anymore, but you certainly will find switches. Switches have been around for quite a while now, and chances are you're probably connected to a switch right now, either a standalone switch or one that's maybe built into some type of routing device. But nonetheless, you're using modern switching technology and modern switching protocols. Now, a switch is a little different in that whereas a hub is a layer 1 device, it's purely a physical device that forwards electrical signals to other ports. A switch is actually a layer 2 device. So it's a data link layer device. And you see I have MAC here in parentheses. And I say that because generally it's going to be based on MAC addresses to get communication where it's going. So Switch actually has software built into it, and that software is programmed to look at the MAC address, the source and destination MAC address for data being transmitted, and then it only sends the data to the host that it's destined for. So this is different a little bit from hubs, which send traffic to everyone, and only the host that wants it would accept it. A layer 2 MAC-based communication switch would send data only to the device that needs it, right? And so this is, instead of broadcast, we're talking about unicast communication now becomes possible. So I'm only sending things from the device I have to the device that I want to receive it, and that's illustrated by this image here. You see, once again, we have 4 computers. We have computer A is sending to computer B, but computer C and D never see the traffic, and that's great, right? That's great from both a performance perspective because we're not sending data to hosts that don't need it, and it's also great from a security and privacy perspective because now computer C and D can't easily intercept the packets between computer A and computer B. That conversation is a little bit more private. So again, this works by the switch examining the MAC address of the incoming and outgoing packets. There's a table on the switch. It's called a CAM table, where the port is mapped to the MAC address. So that information is observed and found through observing packets on the that are already passing through the system and through things like that. So the ARP protocol, we'll talk about that a little bit more later. But it builds this CAM table, which associates these MAC addresses to specific switch ports, and that allows it to forward traffic to the correct location. So again, a lot more efficient. Now, the thing about this is it's also, while it's more efficient and better from a security perspective, it also makes it harder for us to collect packets. Whereas with a hub, you could just plug in and see all the communication between all the hosts. Switches are a little bit different. Therefore, our visibility looks a lot different too. For hubs, our visibility window covered everything. For switches, our visibility covers only the sniffing device. So in this case, we have computer A, B, and C, and we have our sniffer. If I launch a packet capture tool like Wireshark on my sniffer, as per this image, I will only be able to see traffic to and from my device. I won't be able to see conversations between computers A and B or computers B and C, only to and from my device. So if I'm communicating as the sniffing device, if I'm communicating to computer A, I'll be able to see that communication. But if computer B is communicating to computer C, I won't be able to see that. So the visibility window, again, is limited to just my system. Great from a performance perspective, great from a security perspective, makes it a little trickier for us to be able to capture packets. Now, that's not to say there's no way to see packets between other devices on the network, but we're going to have to do a little trickery to get there, or use some hardware, and we'll talk about that a little more later. But again, the big takeaway here is switches, a lot more modern, a lot more performant, but they do limit our ability natively to capture packets and see what's going on the network. Next up, we're going to talk about routers. Routers are primarily responsible for connecting multiple networks together. This is different from a switch, which is designed to connect devices together within a single network. When you communicate with a device on your network, you're communicating over a switch. But when you're communicating with a device over or to another network, you're also communicating over a router at that point. Now, I say also because you're probably using a switch to communicate with the router itself within your network, and then that router is going off and communicating with other routers based upon the traffic you've sent. Ultimately, the entire internet, when viewed simplistically, is nothing more than a collection of a lot of routers connecting various networks together. Of course, there's a lot that goes into making that happen, but from a hardware perspective, it's really routers doing all the hard work. Now, let's look at the image I have on the screen here as an example of how routers communicate. Here, we have two networks connected together via routers. The network on the left contains computers A, B, and D. The network on the right contains computers C, E, and F. If computer A wants to talk to computer B inside the same network, that's pretty easy, and that would occur over a switch like we previously talked about. However, if computer A wants to communicate with computer F, it has to communicate with the router at the edge of the network, which then communicates with the router at the edge of the remote network to route the packet appropriately. So the routers are communicating those things between each other at that point. When you communicate over the internet at any given time, your packets are probably traversing 7, 8, maybe a dozen or more routers to get to where they're going. Very similar to what's depicted here, just at a larger scale. Now, routers are layer 3 or network layer devices, and they communicate in most cases using IP addresses to route packets. Your computer has an IP address, the computer you're communicating with has an IP address, and every router along the path between those two, that source and destination, has 2 IP addresses. So why does a router have 2 IP addresses? That doesn't necessarily make sense, does it? Well, remember that the purpose of a router is to bridge communication between 2 networks. That means it must be able to communicate on both networks using a valid IP address for each network. To support this, a router has an internal network interface and an external network interface, and each one has an address. The internal interface has an IP address matching the IP scheme of the downstream network, and the external interface has an address matching the IP scheme of the upstream network. The router is essentially routing the packet from downstream to upstream or vice versa, which is from one IP space to another. It's bridging the gap. And to do that, it has to have that internal and external interface, which allows it to communicate on both sides using different addressing schemes that could be very similar or they could be very different schemes. It doesn't really matter, but nonetheless, it does have to have both of those interfaces to really work together. Now, I describe routers specifically because the key consideration when it comes to visibility with routers is less about a visibility window and more about the addresses found in the packets we're capturing. And I'm going to talk a little bit about IP addresses and things. We're not going to go too in-depth on IP. We'll talk about that in a dedicated lesson later. But I mentioned that routers have 2 interfaces and must be able to communicate on both upstream and downstream networks. To do this, they use a function called network address translation, or NAT. Now, I want you to consider what communication might look like when traversing a router, and I want you to do that using the image I have on the screen here. Here, we have computer A attempting to communicate with computer D, which is on another network. Computer A is downstream from router A, and we have network taps on both sides of the router sniffing both the internal and external interface. Now, we haven't talked a lot about taps yet, but for this exercise, just know that it's a hardware device that sits on a network link and intercepts packets and sends them to a sniffer, and those sniffers are also depicted here. So we'll go more into taps later. Now, for this example, here, computer A has an IP address of 192.168.1.100, which is in the IP address range used by the internal network it belongs to. Similarly, router A has an internal IP address in this range for its internal interface on 192.168.1.1. That's its internal IP address. If router A were to take a packet sent from computer A and forward it to the next upstream router with a source IP address of 192.168.1.100, what do you think would happen? So if it actually just took the source IP address of the transmitting system and sent that along, what do you think would happen? Well, the destination device would have no way to send a response back. That's because the 192.168.1.100 address is the internal network range for computer A's network, and the network upstream has no knowledge of that address space. right? Those two networks don't know about each other. The only device that knows about both of them is the router. Those upstream devices can't communicate with the internal device directly. It can only communicate with the router upstream from the 192.168.1.100 device. And furthermore, 192.168.1.100 is a non-routable address. It's part of a specific range of addresses designed for use in internal networks only per RFC 1918. So there's a small group of addresses there, and they can't be routed out on the internet. So even if we wanted to route this, we couldn't. So how do we remedy this issue? Well, when the router receives the packet from computer A, so the packet being sent from A to computer D, it actually takes the packet and modifies it. It rewrites the source address of that packet so that it can forward it using its external interface. The packet that did have a source IP address of 192.168.1.100 will now have a source IP address of 203.0.113.45, which is the same as the external interface of the router. The router essentially takes responsibility for the packet and sends it as its own. That way, whenever another device on that upstream network segment needs to send a response back, it will go to the router. The router itself will maintain a record of the packets that it's rewritten that source address for in the open communication streams, and then it will take the response packet that comes back, rewrite the destination address again so that it matches the address of computer A, and it forwards it along through a switch and eventually to computer A so that the communication can complete. And this is all happening through the router's internal interface. So that was a lot to explain, but the summation of all that is anytime you send a packet that gets routed to another network, every router it goes through rewrites the sending device's source address with its own address to ensure that it can actually forward the traffic back correctly and communicate on the upstream network appropriately. Now, this is important. I don't just say this just to give a networking overview. I say this because it's important for capturing packets, because if you capture the same packet at two different locations, that is downstream and upstream from a router, you'll actually see different information in the packet. It's going to affect your visibility and the context associated. Specifically, the source address is going to be different. Remember, that's what's being rewritten. That means if you capture packets upstream from a router, you'll have no way to determine which actual computer the packet was transmitted from. Even if you have 1,000 computers on your internal network, every source address for transmitted packets captured upstream from the router will be that of the router's external interface. They'll all look the same. This means that in most every case, you're going to want to capture packets downstream from the router containing the systems you're interested in. This is illustrated here in this image with the two different sniffing devices we have. The sniffer downstream or to the left side of the router shows the transmitting device's true internal IP address of 192.168.1.100. The sniffer upstream from the router captures the forwarded packet, which has a source address of the router's external interface, so the 203.0.113.45 address. So again, if you capture from this upstream router on the right side here, you have no way, again, of knowing what the true source IP address of the traffic is. Now, once again, all that might be a lot to take in if you don't know a ton about routing. This isn't meant to be an in-depth, exhaustive overview of the routing process, but really more of a refresher so that you can understand why routing matters for packet capture and why routers as a device make a difference in terms of where we place our network capture devices. This course is, of course, a packet analysis course and not a network course. So if everything I've just said was complete Greek to you, if you didn't follow any of it at all, I'd recommend after you watch this video, taking a break, maybe doing some research on network routing and how that works, and pulling in some additional resources so you can understand that. This is certainly very important to understand upstream, downstream placement of packet collection tools so that you're getting the things you need to see, especially if you're doing things from a security perspective or a 24/7 packet capture scenario for network security monitoring. You want to make sure you understand upstream, downstream placement of packet collection devices. But again, for the most part, you're almost always going to want to make sure you're downstream from the router that contains the device that you're concerned about collecting the communication for. So we talked about all those routing concepts. We also talked about IP addressing. Don't worry about IP addressing too much. We have a dedicated lesson on that later on in the course. But again, we just want to make sure you understand this upstream, downstream concept as it relates to routers, which is really the most important thing here.